I'm not going to get too deep into the theory here, but we're going to be talking about the orthogonal complement and how to obtain it. And it can be denoted with this symbol here, V, and then this perpendicular sign here. And more or less what it is trying to find the vector that is orthogonal to the vector that we're talking about. So let's say we have this vector 2, 3, and we map it out on a Cartesian plane. We go over 1, 2, then we go up 1, 2, 3, just, eyeballing it here, not really drawing a great picture. But we want to find the vector that will create a 90-degree angle with this vector. And you can probably tell that there's more than one. Both of these would probably create a 90-degree angle with this vector right here. But essentially what we're looking for is the values where the dot product is going to be equal to 0. And I briefly touched on the dot product in the last video, but hopefully in order to complete a dot product, we would have 2 times x1 plus, and then we would have 3 times x2, and then we want this entire thing to be equal to 0. And this really isn't that hard to kind of eyeball and think it through. You can start plugging in numbers 1, 2, 3. Eventually you can probably tell that if x1 is -3 and x2 is +2, then that will give us 0. Or if x1 is +3 and x2 is -2, both of these will give us the answer of 0. And it's true that if you have a vector of the form a, b, that the orthogonal complement is just going to be -b, a, or it's going to be b and -a. So one orthogonal complement for v should be -3 and 2. And again, you can draw that out on a graph, go over 1, 2, up 1, 2, 3, and then here we would go to the left 3, and then up 2. And conversely, if we were to go 3 and -2, we'd go over to the right, down 2, so we would have something like this. And again, we see that we have those same perpendicular lines that we were looking for earlier. Now to make it more complicated, let's say that B is a span of these two vectors. Now these vectors are linearly independent, and because we have 1, 2, 3 rows, that means that B is a two-dimensional subspace of R3, right? This is going to be R3. And the main thing to know is that the orthogonal complement is going to be one-dimensional, because when we combine these, it's always going to equal to whatever this is. So let's say that we have Rn, which n can be any number. The dimension of B plus the dimension of the orthogonal complement is always going to be equal to n, whatever n is. In this case, n is going to be 3. We see that we have 2 dimensions here. Therefore, the orthogonal complement is going to be one dimension. So real quick, I'm just going to rewrite this as a matrix. 1, 2, 1, 3, 1, 2. And in order to get the orthogonal complement, all we need to do is transpose the matrix. So we're going to turn all the columns into rows. So we're going to end up with 1, 2, 1, 3, 1, 2. All we had to do was swap out all the columns with all the rows. From there, we just need to get this down to reduced row echelon form, because of course we do. We can do row 3 plus -3 times row 1. That should give us 1, 2, 1. 3 plus -3 times 1, that's going to be a 0. 1 plus -3 times 2 is going to be a -5. 2 plus -3 times 1 is going to be -1. I'm going to go ahead and divide this by 1/5 of row 2. So that's going to give us 1, 2, 1, 0. Let me go ahead and make this a negative, by the way. So that's going to be +1, and that should be a +1/5. And row 1, we want to get rid of this 2. So what I'm going to do is take row 1 minus 2 of row 2. Sorry about the sudden change. I had audio problems that I had to fix, so I'm picking up where I left off here, but this is our matrix. We're going to take row 1 and replace it with row 1 minus 2 times row 2. So what we're going to do is we're going to take 1 minus 2 times 0, which is going to be 0, so that's 1. 2 minus 2 times 1, which is going to be 0. 1 minus 2 times 1/5, so that's going to be 1 minus 2/5. And then the bottom row is going to be the same, so 0, 1, 1/5. And then this is going to be 1 minus 2/5, which is 3/5, so we're going to end up with 3/5. Let me replace that. And now we have our pivots here, so we're at our reduced row echelon form. And we want to set this to 0 because, again, we're looking for when the dot product is equal to 0. So we have our x1 plus 3/5. x3 is equal to 0. And then our second equation is going to be x2 plus 1/5. x3 is equal to 0. And now if we just move everything over to the right, we get that x1 is equal to negative 3 over 5 x3, and x2 is equal to negative 1 over 5. And we can see that x3 here is a free variable. So I'm going to write this in the form x3 and then negative 3 over 5 for the first one, negative 1 over 5 for the second one, and then 1 for the third one. And then this is going to be our answer that we were looking for. And we can actually check to make sure that these are orthogonal. What we can do is take our answer and multiply it times each one of these. We're doing the dot product, not a regular matrix multiplication here. So we have 1, 2, 1, dotted with negative 3 over 5, negative 1 over 5, and then 1. And we can see here that we have 1 times negative 3 over 5. That's going to be negative 3 over 5 plus 2 times negative 1 over 5, which is negative 2 over 5 plus 1. So we have negative 1 plus 1, which is going to be equal to 0. So that checks out. It's correct. We can do the exact same thing with 3, 1, 2. So 3, 1, 2, negative 3 over 5, negative 1 over 5. Now I'm not going to write it all out, but we have 3 times negative 3 over 5. That'll give you negative 9 over 5. And then 1 times negative 1 over 5, so that'll be a total of negative 10 over 5 when you add those two together, which is the same thing as negative 2, and then here we have 2 times 1, so that'll be negative 2 plus 2 is equal to 0. And we can see that we have our correct answer.